Hello and welcome to Empowered Learning. This is the second part of the video on calculating volumes of a solid, where we're actually doing solids of revolution, where we're taking a defined area that's bound by some curves and rotating it about a horizontal or a vertical line. And so in our next example, we want to use the washer method to find the volume of the solid generated by the shaded region about the x-axis. So to be clear on this, we know that we're going to use the washer method because there's a gap in between the area and the axis of rotation. We said that the axis of rotation was the x-axis, so that we know that we're rotating about this axis here. And so because of that, we know that the outer radius is going to be from here all the way down to the x-axis. And we know that the inner radius will be here. And so, of course, the outer radius, if we wanted to get technical here, we can define, let me put it here. The outer radius will be the distance in between this function y equals 4 and the x-axis. So it'll be 4 minus 0, which is just 4. That's one way you can think about it, or you can just say this total distance is 4. For the inner radius, we know that the inner radius is going to be from the x-axis to the height of this function here. So that would be 4 times square root of cosine x minus where the x-axis is, which is 0, which just gives you this. And of course, I know that most of you are like, why would we write the 0? I'm just doing that to stay with the convention of one of the ways that we can define the radii here, or a radius, I should say, is the difference in between how far you go out from the axis of rotation and what the axis of rotation is. And of course, in this sense, this is y equals 4 times cosine of 4 times root cosine x. And of course, the x-axis is y is equal to 0. So that's why I'm doing that. All right, so with that being said, we know what our inner and outer radius are. We also know that our limits of integration will be from negative 1/2 to positive 1/2 because this area is bounded by that, okay? Also note that what we end up having here, both functions actually end up being symmetric about the y-axis. So although our volume here can be defined from A to B of pi times square the outer radius minus square the inner radius, dx in this case, we could really just say this is going to be 2 times 0 to b, and of course pull the pi on the outside here and have that be the difference in between the outer and inner radius times dx there, because that would make life a whole lot more simple. Okay, so we know that the area that's here is going to be the same as the area here. So the volume that's created from x equals 0 to pi over 2 will be half as much as it is from negative pi over 2 to pi over 2. So we could go about it this way. So we have everything that we need. We just need to figure out what the square of the outer radius is, which of course in this case will be 16, and the square of the inner radius. And if we square 4, that's 16. If we square root of cosine x, that's just cosine x. So all we have to do is just plug everything in. So this will be 2 pi 0 to pi over 2, and that will be 16 for the outer radius squared minus 16 cosine x, all that dx. Of course, if we want to, we can factor out the 16 if we want. So that'll be 16, 0 to pi over 2. That'll just be 1 minus cosine x dx. So that'll give us 32 pi here. When we take the antiderivative of 1, that's just x. Take the antiderivative of cosine, that is just sine. And we will evaluate that from 0 to pi over 2. So we start off with pi first. So that's pi minus sine, pi over 2 minus sine of pi over 2. Minus, and then if we plug in 0 for both x and sine x, we get 0. Okay. And so we know that sine of pi over 2 is just 1. So we have this. And so now, when we look at this, we can go ahead and multiply 32 pi in. If we do that, distribute it to the first term, that'll give us 16 pi squared minus 32 pi. Of course, if we plug that into our calculator here, we will roughly get 57.38 cubic units. And so, as you can see with this problem, we were given the graph, so it makes doing the problem a whole lot easier to do. So let's move on to the next example. All right, so for this next example, we're asked to take this area that's in between the y-axis and this curve here, x is equal to 4 tangent of pi over 6 times y, and we want to rotate this shaded area about the y-axis here. So we want to take this, rotate it about the y-axis. And so what that looks like is we want to have some shape that kind of looks like this, but kind of doing it like this. So it looks like that's what the shape of this is going to be whenever we rotate everything. So just so that we kind of have an idea of what this is going to look like. So one of the things that I hope you notice here is that to be able to rotate this about the y-axis, there is no gap in between the y-axis and the axis of rotation. So that means here we can actually use the disk method. And you may spell disk this way, or you may spell it this way. But either way, the disk method will be used here. Okay. And for the disk method, we know that the volume here, here our area is just going to be pi radius squared. And since we're rotating about a vertical line, that means we're going to integrate with respect to y. So here this will be from C to D, area in terms of y dy. So what we need to do now is actually figure out what our area is going to be defined as, okay? And so, of course, if we look here, our radius here is just going to be defined by what the x value is here. So this is our radius in terms of y, okay? And let me go ahead and put this here just so that we're clear. The area here is pi r of y, quantity squared dy. And of course, r of y is going to be the same thing as x is. So here, 4 tangent of pi over 6y, that's going to be what our radius is there. So this one is relatively simple, and we're going to integrate from x equals 0 to x equals 1. All right, so let's go ahead and continue on. So come here, and this will be from 0 to 1 of pi. And of course, if we're taking this and squaring it, we know that 4 squared is 16, and tangent of pi over 6y squared is just going to be tan squared of pi over 6y, all that dy, okay? So we will factor out the 16 pi, 0 to 1, tangent squared of 6 pi over 6y dy, okay? Now, when we look to try to take the antiderivative of tangent squared of pi over 6y, just focusing on the tangent squared, we don't have anything that will give us a direct antiderivative for that. But what we can do is use some of our trigonometric identities to rewrite tangent squared in another way. And so in particular, we know that sine squared plus cosine squared is equal to 1. And I'm just going to let S equal sine of some angle and C be cosine of some angle. So if we were to divide both sides by cosine squared, then what that would turn out to be is tangent squared of some angle plus 1 equals secant squared of some angle. And so we see here we have tangent squared there. And so from that, we know that secant squared of some angle minus 1 will be the same thing as tangent squared of an angle. So here we could rewrite tangent squared of pi over 6y as just secant squared of pi over 6 times y minus 1. And we do have a direct antiderivative for secant squared because we know that the derivative of tangent is secant squared. And so because of that, we know that the antiderivative of secant squared is just tangent. So if we rewrite this using this identity here, then of course everything else will be pretty easy to do from this point. So that's what we'll go ahead and do. So I'll go ahead and erase this and then continue on with the problem filling in that particular trig identity. So we're here and have 16 pi, integrate from 0 to 1, and we will have secant squared of pi over 6y minus 1. All of that. Whoa, didn't mean to do that. I just wanted this to look a little better. So we got here all that dy. So now from there, I'll separate this into two separate integrals, since for this first one here, we probably end up having to do substitution to make that easier. So I'll say this is from 0 to 1 of secant squared of pi over 6y dy minus 0 to 1 of dy. Okay, and matter of fact, I think I will just stop this here. And so let's handle this part first. So let's let u equal pi over 6y. And so that will imply that du is going to just equal pi over 6, or du over dy will be that. And so according to substitution here, if I replace pi over 6y, I just need to replace dy. So if I do that, multiply both sides of my equation by the reciprocal of pi over 6, which is just 6 over pi, and multiply both sides by dy, what I end up with is this scenario here. Okay? So I know that 6 over pi du is the same as dy. I also know that I can change my limits of integration here. Let's get that working. And I know that u of 0 would just be like plugging in 0 here for y times pi over 6, which will be 0. And I know that if I plug in 1 for y, that would just be pi over 6. So for this first term here, I know that I can change the way that that looks. So here we have, therefore, 16 pi, and then instead of saying from 0 to 1, now that's going to be from 0 to pi over 6 of secant squared u, and that'll be du, and of course there is a 6 divided by pi factor that's on the outside there, okay? Now for the second term here, pretty much will stay the same. It's not much to do with that, and we know that integrating dy from 0 to 1 will be relatively easy here, okay? So from this point, we know that integrating secant squared of u would be the same as tangent of u, and that will be evaluated from 0 to pi over 6. And then minus, we have 16 pi, and we will integrate dy, which is just y, and that will be evaluated from 0 to 1. Now what we'll do is just finish out this problem here. So we have our 16 pi times 6 over pi. Of course, the pi's here will reduce to 1. So that'll just leave us 16 times 6, which is just 96. So we'll go ahead and do that. And then evaluate tangent pi over 6, and then evaluate it also at 0. So tangent of pi over 6 minus tangent of 0. And then we'll do the same thing for 16 pi. And for y, that will be 1 minus 0 there. And so tangent of pi over 6 is 1 divided by root 3. And we get that. Let me do this over again. So some of you remember the unit circle. Others of you may remember the right triangle relationships. And so that's how I remember it. So here we know from a 30, 60, 90 triangle, this is a proportion to the sides. So tangent is tangent of 30 degrees, or same as tangent of pi over 6 radians. It's just 1 divided by root 3. So here that is what that would be. So I'll put the equal sign here, 1 here, and erase this. And so that would be 1 divided by root 3. And tangent of 0 is 0. And of course, here we just have 16 pi. And just so that we know, 1 divided by square root of 3, if we rationalize the denominator, would be the same as root 3 over 3. And so I'm going to go ahead and change this to that so that we can have all rationalized denominators. So square root of 3 over 3 there. Okay. So now we know that 96 divided by 3 is just 32. That's root 3 on the inside there, minus 16 pi. And so this would be our answer. If you wanted, you could factor out the 16. And if you did that, that would just end up being 2 times root 3. Sorry, 16 times 2 root 3 minus pi. So that's what that would be here if you wanted to do it that way. And so either one of these answers is the exact answer for this one. Okay. And if you're asked to give an approximate answer here, let's say if we round this to 2 decimal places, this would be approximately 5.16 cubic units. Okay. So that's how we do this particular example. So this will conclude part 2 of the videos on trying to calculate volumes of a solid by solids of revolution. Part 3 of this video will be another example to where we break it up and we have the same type area, but we're going to rotate it about 3 different axes. And so by changing the axis of rotation will also change whether we're going to use the disk method or the washer method, as well as if we have the washer method, how we're going to define the inner radius and the outer radius. So if you're interested in those examples, check out my next video.